SwayamPrabha. Digital India. Educated India.
So last class we started to do explaining that what is the disjoining pressure, what is the value of the disjoining pressure, and if a certain liquid actually wets a particular solid wall, what are the different regimes. So if you recall this particular part of the presentation, what we had was that there was a liquid which wetted a wall over here, this is the wall, okay, and this is basically after this the liquid basically continues. So it is like a wetting, it is like completely wets the surface, it is like an extended meniscus. So up to this region, from this region onwards, it is called the thin film region, okay. So thin film region, we already established what the thin film region is, that what is the magnitude of the thickness of the film thickness that is needed. So this is the thin film region. Now in the thin film region there exists a non-evaporating equilibrium thin film region where the wall temperature is the same as the liquid temperature, okay. Then there is a microfilm region, okay, where both the capillary pressure as well as the disjoining pressure plays a major role, okay. Here the film temperature is greater than the saturation temperature, but lower than the wall temperature. So this is called the microfilm region. Here the flow is basically driven by both capillary as well as by the disjoining pressure, okay. And so it is driven by the curvature as well as by the disjoining pressure, that is what we wrote, okay. Then there is a transition region basically, and then there is a thick film region which is the meniscus region where the temperature of the film is the same as the saturation temperature, okay. And here because of the large thickness of the film, okay, the disjoining pressure does not play much of a role, okay. And we also established the fact that as the thickness of the film goes up, the disjoining pressure effect comes down. And if you recall this graph over here, you can easily see that when the film thickness is about 5000 nanometer, which is 5 microns, okay, the human hair is about 100 micron. So it is basically 1/5 of the, rather 1/20th of a human hair, okay. So that is the thickness that we are talking about. When the thickness of the film is like that, the disjoining pressure is basically practically equal to 0, that means it is virtually negligible, okay. So in the microfilm region most of the evaporation actually takes place, it is ideally suited for that, okay. But in another case, okay, another interesting question that pops up while we are doing this analysis is that what is the nature of the saturation vapor pressure over a curved interface, right. So this is a curved interface, that what we see over here, right. What is the saturation pressure looks like, okay, how is it influenced, okay. So let us look at that in details, okay. So let us look at the journal part now, okay. Now in the thin film region, so our question that we are going to answer is that what is the nature of the saturation pressure, right, how the saturation pressure is changed across the interface, whether there is a suppression of the saturation pressure or not, okay. So my initial statement will be the disjoining pressure and the capillary effect, okay, reduce the saturation pressure okay, compared to normal conditions. Okay. This is a statement and we are going to prove this particular statement, right. So what we are saying is that both the disjoining pressure and the capillary pressure has an effect on the saturation pressure, right. Okay. Now, the thin film region, we are only talking about the thin film region over here, delta. Okay. The liquid interface temperature okay, is T delta, right. So, the normal saturation vapor pressure will be vapor pressure will be P sat, whatever is the saturation pressure corresponding to that temperature, and you can almost look it up from the thermodynamic table, right. You know the temperature, you can find out what is the corresponding saturation pressure. So, we are stating that the liquid interface temperature is T delta and the corresponding saturation pressure is P sat T delta. Okay. And we are going to say that whether this pressure, okay, the actual saturation pressure, whether it is different from this or not. Okay. So, recall, if you do a little bit of recall of your thermodynamics, okay, at equilibrium, remember we are only talking about equilibrium over here, we are not talking about a receding or an advancing liquid front, okay. We are not talking about that. Mu L is the same as mu V, right. That is what we proved earlier, got it, okay, at equilibrium, right. So, the chemical potential of the liquid and the vapor phases should be the same. Now, integrating the Gibbs equation, okay, which is basically nothing but this, and we integrate it at constant temperature, got it, okay. So, this is the Gibbs equation, okay. Once you integrate it at the constant temperature, this term basically vanishes, right, because it is a constant temperature integration. So, it is mu minus mu sat is equal to P sat at whatever the delta is to P V dP, correct. So, this is basically the mu minus mu sat when integrated, okay, that is basically integrating this term, you get P sat to P, okay, this is the arbitrary limit of integration. Okay. Now, there are two other things that we would like to mention. One is that your Vb, that is the specific volume, right, of the vapor phase, is given by Rg, sorry, it's Rg T delta divided by the corresponding PV, correct. Okay. Now, that is the volume of the vapor phase, right. Vl on the other hand is equal to V, okay, for the liquid phase, assuming that the liquid is incompressible, got it, okay. So, now we can write basically two sets of equations for the liquid and the vapor. So, the mu of the vapor phase, okay, at delta is equal to mu sat mu sat V plus Rg T delta ln PV delta divided by P sat T delta, got it. That is the first set. Okay. Now, the second set, mu L into delta is equal to mu sat L plus VL PL minus P sat T delta, got it. These are the two sets of equations, right. In one case VL is incompressible, so it is constant, in the other case it is not. So, we are integrating it, right. If you have not understood it, let us go through it once again. So, mu minus mu, this is a common equation, right. Okay. So, this integral is a common equation. Now, the vapor volume, as you can see, is a function of the vapor pressure, correct, that comes from the so this particular equation is well known, right. On the other hand, for the liquid phase, okay, we are assuming it is incompressible. So, it is basically a constant. Okay. So, you integrate this equation, one for the liquid phase and one for the vapor phase. Once you do that, okay, you get two sets. One is for the vapor, okay, where you have a change in that volume, right. The volume has been substituted by the corresponding pressure form, and in the other case you get it just simple in terms of VL, because VL is constant, you can take it out. Okay. So, it is a very simple integration. So, now, so you have now two sets of equations over here. Okay. Now, let us try to do a combination of the two now. So, it is P sat T delta into exponential VL PL minus P sat T delta divided by R delta T delta. Got it? When you combine the two forms, that is what you get. Okay. So, the pressure difference now in the liquid and the vapor phase, okay, can also be given as right, because this is the capillary pressure, this is the disjoining pressure. Capillary pressure comes from the curvature effects, that is, as we said, for a flat interface this should have been the same, right, whereas the disjoining pressure comes because of the thinness of the liquid film. Got it? So, using these equations we eliminate PL. Okay. So, once you eliminate PL, so what you get is P sat T delta and you can work out the math, the details, the algebra part, that is PD got it. Okay. So, that is the net expression that you get. Okay. Now, if the interface is flat, okay, and thick. So, the interface can be both flat and thick, right. So, it is like you have a bucket full of water, that is like a typical interface which is very thick, right. Okay. So, in that particular case, when the interface is thick, you get PD is equal to 0, right. If PD is equal to 0, only if it is a thick interface, but it is not necessarily flat, you get PV delta is equal to P sat T delta, and you have the expression which is basically PV delta minus P sat T delta minus P cap, okay, divided by rho L R G T delta. Got it? Okay. So, there is a reduction, and when the interface is flat, you know that all the terms basically vanishes. Okay. When the interface is flat and thick, you basically have your P delta is the same as your saturation pressure. Okay. When both of these things happens, right. So, in general what you see is that the vapor pressure, saturation vapor pressure at the interface is actually lowered compared to the P sat, right. So, what we can say over here is that there is a reduction in saturated vapor pressure compared to P sat, right. So, compared to P sat, okay, there is a reduction, this is P sat, okay, compared to P sat there is a reduction in the saturation vapor pressure. Got it? Okay, because of this factor that sits here, right. So, what does the curvature do? The curvature, if there is a disjoining pressure and a capillary pressure, there is a definite reduction of the saturation pressure near the interface. Even if there is no disjoining pressure, there is a reduction in saturation pressure at the interface because of the normal curvature. And if the interface is however flat, you however recover the old form. That means your saturation pressure and your normal saturation pressure, which is given by this, is the same as the saturation pressure across the on the other side of the interface, right. Okay. So, here therefore, in this particular part of this particular lecture, what we have done is that we have covered that how the interface actually, what will be the pressure difference across the interface, right. And we also know now which part of the interface should evaporate, which part of the interface should not evaporate, which will be what kind of a curvature will actually govern the flow, and we have defined a very interesting quantity which is the disjoining pressure over here. So, take away from this particular section is PD and P cap, okay. And these are very important in many applications, okay, especially for thin film dynamics. Okay. When you do materials processing also, like for example polymers, thin polymer films, okay, you would have a lot of role of the disjoining pressure over there. Okay. We have not gone into the intermolecular perspective except giving an idea that this is governed by the Lennard-Jones potential 612 potential, or you can adapt a form like that. But apart from that, we have not gone into the details of working out, okay, but we have said it arises out of the dispersive as well as the electrostatic forces, right. But that is not needed also, because this is not a full fledged statistical mechanics class, okay. But what we have done over here is to provide you with an overview that how to attack, okay, a problem like this where you can have an effect of the disjoining pressure. Okay. Now, having done this, let us look at some of the interesting conservation laws that we wrote earlier, right. We wrote this conservation laws in terms of, if you recall, if you recall the interfacial heat and mass transfer lecture, right. What did we do over there in the interfacial heat and mass transfer lecture? We did not include the effect of surface tension and disjoining pressure effects, right, when we actually did it, when we wrote the interfacial equations, right. So, let us now include those things over here, okay, because once you include those things, now you can have a holistic view, right, of the interface. So, let us look at the mass balance first, and I will not go through the details of the math, I will just write down the basic equations, right, at the liquid vapor interface, right. Once I write it, you will recall that what I wrote earlier. The mass balance is given by, okay, do you recall this particular form VL minus VI, right, dot N, right, okay, that is the interface, that is the reference speed of the interface, to rho V Vb minus Vi dot N. Okay, this is the mass flux at interface due to phase change, if you recall. Okay, Vi, this is just to recap, Vi was the interface velocity, right. Okay. Now, this is the normal component of the velocity, this is the first tangent, this is basically the second tangent, because you know it is a 3D interface. Interfaces are normally 3D, right, it is a 3D interface. So, basically you need one normal and two tangents, right, to define it, got it. Okay. So, now the mass balance, therefore, write it rho L PLN minus VIN equal to rho V PBN minus VI N. Okay. So, that is what we have for the in terms of the mass balance, and we have included the 3D nature of the interface over here, right, okay, by combining all these terms. Okay. that is a mass term. So, now let us look at the momentum balance. So, the momentum balance okay. So, the momentum balance, if we start writing out the momentum balance, now the momentum balance that actually includes all the surface tension forces, right, because it should come from the momentum balance over here, right. Okay. Now, normal momentum balance will be something like this. It is very similar to the mass balance, right, except now this is a change of momentum is equal to the forces. Okay. Now, let us include this, we knew already, let us add the two effects, surface tension and PD effects. Okay. So, this gets added to the left hand side of this equation, to this side of this equation. So, what do we have? Tau L minus tau V prime dot n plus sigma T. If you recall already that sigma T was responsible for that Marangoni flow and related things. So, this is like Ri plus 1 by R2 and minus PD into n, okay, PD being the disjoint. I will go across to each and every term over here, d sigma by dt. This is where the Marangoni stress term comes into the picture, VL minus VB. Okay. Now, let us look term by term. This is basically nothing but the stress tensor, right. This is stress tensor, we all know this. Okay. This is basically nothing but the capillary pressure, which we covered, right, the capillary pressure, right. This is basically the disjoining pressure, only happens for thin film, correct. Okay. This is basically what we call the Marangoni stress, because you have this gradient, right, d sigma by dt. Okay. So, you have a Marangoni stress, okay, if there is a temperature variation, right, and this is basically the momentum transfer due to inertia. Right. So, as you can see, when there was no, if the interface is flat, say for example, absolutely flat interface, this term will go off to 0, correct. The second term will go off to, this will only come when there is a curvature, right. If there is no curvature, why should the term actually be retained? If the film is very thick, the disjoining pressure will go. If there is no temperature variation, right, okay, this term will also go. So, we would go back to our original formulation across the interface, right. So, if it is a straight flat interface and thick one, right, okay, if this is thick, okay, then of course, your equation boils down to basically that, right. Moment you have a curvy kind of an interface, right, you actually are including this term into the picture. If there is a temperature variation from here to here, okay, say that can happen because say you have a heater, okay, you have a differential heat flux, say the temperature is increasing or you are supplying heat to this substrate in this particular fashion, right. What will happen? This surface temperature will also start to vary, right. Because of that, you will actually have a variation of the Marangoni stress, right, across the interface, that needs to be accommodated over here, right. Okay. And if this film is very thin, that means if this delta now becomes much less than say 10 nanometer or 100 nanometer, then you actually bring this term into the picture, right. Okay. So, the momentum equation now basically boils down to this particular, these three additional terms, all of which comes from the curvature, temperature gradient, right, as well as the disjoining pressure, all of which we covered in the previous lectures to give you guys an idea of what it is, right. Okay. Now, this T of course can be T1, okay, and T2. So, that is the two tangents, okay. Now, this tau prime, any tau prime can be written as the pressure plus the 2 d minus 2/3, not all of these terms are retained, into the corresponding I. Okay. In many of the cases, so this is the general form of the stress tensor, right. This we already know from your Navier-Stokes equation and whatnot, right. So, in many cases m triple dot prime, this one, okay, is not high, it is not high, right. That means the other way of saying is that there is no evaporation or condensation or whatever it is that you are talking about. Okay. So, no substantial, I would say, evaporation never stops, right, no substantial evaporation or condensation. Got it? Okay. No normal evaporation or condensation. In that case, what will happen is that your m triple dot VL minus VB, this particular term will be equal to 0, right, if that is the case, corollary of this, right. If the liquid and the vapor phases are inviscid, say for example, right. So, if liquid and vapor phases are inviscid, it can be inviscid, right. In that particular case, what will happen is that tau L equal to tau V will be equal to 0, right, there is no viscous shear, right. Okay. So, in that particular case, the momentum at the interface reduces to, okay, PV minus PL sigma T 1 by Ri plus 1 by R2 minus PD, right. This is we are very familiar with, this is that capillary pressure form, right. Okay. So, in most of the cases you get away using this, because in many of the books you will find that this is what they write, that across the interface this is the momentum balance, right. This is not exactly always true. If there is evaporation, okay, you have to include the evaporation term, that is mandatory, right. If there is viscous stress, you have to include the viscous stress at the interface, but in many cases this may be considered negligible, okay, compared to the curvature effects that we have here. Okay. So, this is basically what we call the revised momentum equation. Got it? Okay. In most of the cases this would be kind of valid. Okay. Now, the follow up will be in the next, we will start with the energy equation. So, the energy equation, and we will see how the energy equation actually varies over the interface, because we have done mass, we have done momentum, we have shown how surface tension and the disjoining pressure enters into the picture, how Marangoni stress enters into the picture. Now, we will do the energy and then correspondingly do the species, right, because these are the other two snippets, right, where we actually have to include these effects over there. Okay. So, that we will do in the next lecture, okay, which follows. Okay. Thank you.